I'm Dr. Roger, and today we're looking at systems of first-order linear ordinary differential equations with constant coefficients, in particular one where the eigenvalues have opposite sign, and we're interested in the resulting phase portrait. So we'll start by setting determinant of A minus lambda times the identity equal to 0 to find the eigenvalues. So A is negative 1/4, 3/4, 3/4, negative 1/4, and then minus lambda times 1, 0, 0, 1 gives us negative 1/4 minus lambda, 3/4, 3/4, negative 1/4 minus lambda. That determinant would be the product AD minus BC for a 2 by 2 matrix. So we're setting lambda squared plus 2/4, which is 1/2 lambda, plus 1 over 16, and then minus 9 over 16, so that's minus 8 over 16 minus 1/2. That's setting the determinant equal to 0. This factors lambda and lambda, 1/2 and 1, and the 1 is positive. Checking FOIL verifies I factored that correctly. Since this product equals 0, either the first factor is 0, so lambda equals 1/2, or the second factor is 0, so lambda equals negative 1. I'm going to call these lambda 1 and lambda 2. Next, we want to set A minus lambda 1 I times my first eigenvector equals the 0 vector, and solve for that eigenvector. So I have A minus lambda I there. I'm going to put in lambda equals 1/2. I get negative 3/4, 3/4, 3/4, negative 3/4 times C1, C2 equals the 0 vector. And if we choose a value for C1, and convenient value is 1, then we can solve for C2 is also 1. So our first eigenvector is the vector 1, 1. There is no unique solution because the second row is negative 1 times the first row. Similarly, if we set A minus lambda 2I, eigenvector 2, equals the 0 vector, we can solve for the second eigenvector. So lambda 2 is negative 1. Negative 1/4 minus negative 1 is 3/4. So we get 3/4, 3/4, 3/4, 3/4 times C1, C2 equals the 0 vector. If we choose a value for C1, and I'm going to choose 1 because that's easy to work with, then C2 is negative 1. And my second eigenvector is the vector 1, negative 1. In some fields, by convention, all eigenvectors have magnitude 1, so you'll divide this by the square root of the sum of the squares of the components, so that would be 1 over root 2, negative 1 over root 2. But in most applications, we don't have that constraint, and it's easier to work with 1 and negative 1. The arithmetic is simpler, it's easier to visualize. Our solutions are x, which is the vector x sub 1, x sub 2, equals e to the lambda t times your eigenvector. So x superscript 1 for my first solution is e to the 1/2 t times 1, 1. And my second solution is e to the negative 2, no, e to the negative 1t, 1, negative 1. Your general solution for all systems, for all linear systems of ordinary differential equations is x equals C1 x1 plus C2 x2, and if you're higher dimension, continue on with your independent solutions. And that gives us x equals c1 e to the 1/2 t 1, 1 plus c2 e to the negative t 1, negative 1. If you want to sketch the phase portrait for this in the x1, x2 plane, where x1 and x2 are the components of this vector x, your class or your textbook may call them x and y rather than x1, x2, but frequently we go with x1, x2 because we often generalize to 3 or 4 or more dimensions. Eigenvector 1 is in the direction 1, 1, which is right 1, up 1. That's a line with a slope of positive 1. My eigenvalue is positive, so I draw arrows indicating I move outward along that vector as t increases. Eigenvector 2 is in the direction 1, negative 1. That's right 1, and then down 1 in the direction x2, a line with a slope negative 1. And as t increases, e to the negative t decreases, so the component in this direction decreases over time. We move inward. I tend not to worry about the relative magnitude of my two eigenvalues if they're different in sign. If I'm not on one of these two vectors, I'll have a linear combination, and my component in the eigenvector 2 direction goes to 0 as t increases because e to the negative t is going to 0. My component in the direction of eigenvector 1 goes to infinity because e to the 1/2 t goes to infinity. So my trajectories will form a pattern that we call a saddle that tends to more or less parallel the closest eigenvector, or at least the direction of the arrows is the same as the direction of the closest eigenvector. So our trajectories look something like this, and further out, they're a gentler curve. It's helpful to be able to draw the trajectories without computer or calculator assistance, but you also want to check that using some electronic computation and help build the precision of your intuitive sketches. Come back soon for my next video. With math, there's always more.